Hello everyone, I am Haritabh. I am an engineer at Superbase and I work on Multigres. Thanks for coming to the talk. Over the next half an hour or so, I want to tell you a story about a problem that sounds a bit boring on the surface, but it turned out to be one of the kind of hard problems in the whole project, and it is probably not the part you would expect. It's not the sharding, it's not the consensus, it's compatibility. So, building a truly compatible Postgres proxy. So, Multigres is a proxy that sits in front of Postgres. And when we started, we assumed that the hard problem would be the classical distributed systems ones. But the thing is that in most of the time, subtle bugs are caused by things which are much simpler and much quieter. So the kind of so with Multigres, we strive to build a whole system which is truly and really compatible with Postgres. So the kind of compatibility where a client is connected to our proxy and it genuinely cannot tell whether it is talking to a real Postgres or not. So this whole talk is about chasing that bar, what it actually takes, and just as importantly, how we measure it, instead of just putting Postgres compatible on a slide. Right? So what is Multigres? A little context. So in one line, it is just Vitess for Postgres. So if you know Vitess from the MySQL world, horizontal scaling, connection pooling, cluster orchestration, failover, etc. That's the shape of what we are building, but just for Postgres. So you don't need to hold all of that in the head today. The only thing that matters for this talk is that there is a proxy sitting between your application and the database. And my job for the next half an hour or so is to convince you that the proxy can be completely invisible. So what is Multigres? A little bit of architecture. So there are two services. One is the multi-gateway. This is the one which sits at the very front and speaks the raw Postgres wire protocol. And that is the one which your clients are directly connected to. That could be your pSQL, your driver, your ORM, anything. Behind that is a multipooler which sits in front of each real Postgres. This owns the transaction and does the actual talking to Postgres part. And critically, between the gateway and the pooler, we do not speak Postgres, we use gRPC. This one decision is kind of the source of basically some hard problems that we will see. Because every Postgres specific thing, whether it is something simple like an error or a result row, or even asynchronous messages, now has to survive this translation going into gRPC and then coming out of it and again reforming itself into a Postgres message. And Postgres protocol and gRPC are fundamentally not equal to each other. They disagree on what is an error, what a result looks like, what an event looks like, etc. And bridging those two worlds is kind of the engineering that we had to do to get it a bit transparent. So let's motivate the problem. Every proxy, every pooler, every connection thing that you can download says on the box that speaks the Postgres protocol. And that is true. Parsing the startup message, parsing a query, that's the easy part and that's the 80% of it. And that, I think everybody does it. But there is a huge gap between I can parse the protocol and the other part, which is I behave exactly like Postgres in every situation. That gap is a long tail of tiny, tiny behaviors and small quirks here and there. And here is the thing about that long tail. When you get one of them wrong, the application doesn't crash in your test environment. It will work fine in the demo. It will probably break somewhere in the middle of the night where some field is missed and some ORM relies on it, and because some library deep in the stack depended on a small detail that you missed. So we needed a definition to hold ourselves to. And here is our definition. An application connected to Multigres cannot observe any difference from a direct Postgres connection along any axis that it can reasonably probe. And then we made that concrete. Every wire message Postgres can send, and just as importantly, only the ones that it would send. Every diagnostic field on every error and every notice, every state transition in the protocol, every asynchronous message delivered exactly at the same moment that Postgres would have delivered it. Every startup parameter, TLS, handshake related quirks, etc. It's a very long list, but the good thing is that defining it precisely and then making it testable is what held us to that bar, and we will see some of those examples in the going talk. It's still a work which is ongoing, so yeah. So when we sat down and actually audited what transparent requires, the list was longer than we expected. And every item on the list sounded very niche in isolation. Who cares about that one field, right? But collectively, they are the difference between a proxy you can drop in front of a real application and the one that quietly corrupts its behavior. I'm going to walk through 4 or 5 of some interesting cases, and there is no particular order here, it's just few examples that I wanted to present. So let's start with probably a simple one, which is the error diagnostic fields. So this crystallizes the problem, which is the error diagnostics, which is that whenever Postgres reports an error, it's not just sending you a string, it's sending a fully constructed wired message built out of some 14 or so distinct fields. It contains the severity, state, message, detail, hint, cursor position, all of those things. And as we saw in the previous architecture diagram that we have a gateway and a pooler and we speak gRPC between them. Now, gRPC basically just gives you one status and one string. So the simple solution would be to just take the Postgres error, flatten it into a string, and move it up. But the moment you do that, you have destroyed a bunch of fields, and real tools depend on those. Like an ORM can't read the SQL state. An ORM that cannot read a SQL state falls back to a regex message text. And the observability tools, etc., that lose the field start lumping completely unrelated errors into one bucket. So we don't do that. Instead, we define our own protobuf, which carries every single application visible diagnostic field, and we attach it to the gRPC status details. So the transition is lossless in both directions. So as you see, the Postgres sends the error to the multipooler, and between multipooler and multi-gateway, we pack it into that gRPC message, and then again we unpack on the other side of it, so that between multi-gateway and the client, it looks as if the exact protocol message that Postgres would have sent to the client. And then we have written a bunch of these round-trip tests which ensure that all of those fields are there. Now, let's move to the next one, the notice messages. It's kind of similar to error, but it's a little bit sneaky because the notices can arrive asynchronously at various different points in time. So they can be informational, they can be a warning, they can be a deprecation hint, etc. And it can arrive even in the middle of a stream of all the rows before the command completes, etc. A lot of tooling do depend on that. ORMs surface them, monitoring systems log them, etc. So the proxy can't just collect them and hand them over at the end. It has to forward each one of them in the order, immediately the instant it appears, with no buffering, because buffering changes the timing the client observes, and the timing is observable. So the way we make that work is, remember, everything between the gateway and the pooler is gRPC. So we model a notice as just another kind of payload inside our gRPC streaming response. So it travels in the same stream as the result row and the listen notify notification, interleaved exactly in the same order that Postgres produced them. The gateway pulls each item off that stream and puts it onto the client connection the moment it arrives. Now, to be honest, there are some limitations because in certain connection teardown races, we have still observed that we are not able to preserve the exact order, but more or less it is done, and the corner cases that are remaining is still something that we are working on. So the bottom line is that we forward every notice we actually see. but we can't promise this delivery for the every single tier down cases. There can be some small niche cases where the trailing notice messages can get dropped. Now the next one is the copy protocol. So here as an example, I have taken the copy from stdin, but the copy to std out, like copy from to works pretty much in the similar way. I've just taken the copy from as an example. So this is the bulk load path, and up to now, everything that we have seen has been a request response kind of thing. Copy is working in a different way. So after the server says, okay, go ahead and send it, the client starts streaming an unbounded sequence of copy data frames. It could be a few kilobytes, it could be some GBs, like it just depends on how long the stream is. And the proxy is suddenly in the middle of a long-lived streaming state machine, not a tidy request response exchange. And both of the naive approaches fail. If you buffer the whole stream, so you forward it in one piece, you fail over on the very first really big import. And if you're chunking the bytes as they flow, then you basically break the framing and lose ordering. So what we did for Multigres is that we model the copy end to end as a full-fledged streaming state machine, just as Postgres intends to do it, with explicit phases in between. So we have a copy entering phase and then the streaming data phase and done or failed, all the stages of the state machine. And the bytes flow straight through both the hops as they arrive from the client to the gateway over the wire. They go from the pooler over gRPC and then from pooler to Postgres over the wire again, with nothing ever completely staged in memory. On the diagram, you can see that the loop in the middle, that's the copy data phase, repeating for as many chunks as it takes. And then the client, and then it cleanly exits. And it works the same way in reverse for copy 2, the bulk export direction. So you can stream like a 50 GB table in or out straight through the proxy, and the memory usage stays flat. Okay, this is one of the interesting ones, which is the cancel protocol. Because the solution is kind of a neat little trick. Let's think about like how the cancellation works in core Postgres. So you're running a slow query on your connection. To cancel it, the client does not send anything on that connection. It opens a brand new separate TCP connection, and on that new connection, it sends a very tiny cancel request message, which carries two things, a process ID and the secret key, both of which Postgres handed it back during the startup when the connection was first created. Right? Now here is our problem. We have multiple gateways behind a load balancer. That brand new cancel connection can be sent to a completely different gateway than the one where our query is actually running. So the gateway that receives the cancel often has no idea that this query even exists, or like this process ID even exists. So how do you route the cancel to the right place? The answer, like we'll see, and it's quite simple. So as you can see from this diagram, we take this 32 bits and we divide it into a gateway ID and the local process ID, and we call it a virtual process ID. So here is the trick, that the process ID we hand to the client at startup isn't just a random one. We encode some information into it. So it's a 32-bit number. The top bits are prefix that says which gateway issued it, and the rest identifies specific connection on that gateway. Let me walk you through the flow. So the setup, the client connects and it lands on gateway A, and it runs its long query. The PID it got back while connecting has gateway A's prefix baked into it. The query is now running, and gateway A to the pooler, pooler to the Postgres, so on. Next, the cancel appears. The client opens a new connection, and let's say it lands on gateway B, which is a which is not the gateway where the actual connection was in the first place. So now B doesn't panic. It decodes the PID, reads the prefix, and goes, well, that's not mine. That belongs to a different gateway. So it looks up gateway A up in the topology and forwards the same cancel as a gRPC cancel query to gateway A. Gateway A receives it, checks that the secret key matches. That's the security check, and you can't cancel someone else's query, and cancels the query context. So this context is the gRPC context for the stream. And then the pooler does the real work, where it issues a PG cancel backend against the actual Postgres backend, which ends up stopping the query. And the client gets back the standard canceling statement due to user request error, the error code. From outside, it looks exactly the PID and the secret based cancel protocol, even though they can land on completely different gateway, and even though there is a cross gateway communication, all of that is transparent from the external client's perspective. So these were some of the examples, and there were many, as I saw earlier, that it's a long tail, and we are still working on those. So just to name a few, there are some quirks around the TLS handshake. Even when the handshake begins, there is a tiny pre-startup negotiation, and there is a CV kind of footgun that around accidentally trusting plain text bytes that got buffered before the handshake completed. There are other corner cases like the startup params for client encoding, search path, time zone, etc. And the extended query protocols describe message has two different forms, one for the prepared statement, one for the portal that Postgres answers differently, and so on and so forth. So now moving on to the next section, which is that how do we know any of this works? Again, the answer is very simple. So at this point, we have made a lot of claims, and we have just said it's transparent, trust me. But why should we, right? So here is the part of the project that is kind of nice, which is that Postgres ships its own regression test suite. That's the PGDay, that has thousands of SQL statements and the diffs and the output against the expected byte by byte matching. There is a sibling suite, which is the PG isolation test. That does the same thing, but for concurrency. There are multiple sessions coordinating, taking locks, waiting on each other. These are some of the strictest correctness checks that Postgres has, and they are literally the tests which gate every single core Postgres release. So our idea was very simple, which is that let's just point the Postgres' own regress suite onto our proxy. If the tests pass, then it's behaving like Postgres. If it doesn't pass, then we will know exactly what's wrong. So now the first thing, so when we initially ran the suite, we got hundreds and hundreds of errors. And initially we thought, okay, wow, so many things are wrong with the proxy. But the funny thing is that it was not the proxy at all. It's just a reminder that GUCs are extremely important. So when it runs in core Postgres, it runs with the default GUCs like the default value for work mem, the default value for random page cost, etc. And we had some different values for some different set of tests. And what it resulted was that even though the output was correct, but the explain was different. And as a result, the regress was failing because it is doing a byte by byte match. The moment we reset those settings back to the default ones, a whole bunch of errors just evaporated at once. The lesson is just a small reminder that configurations is extremely important, so you have to pay attention to that. Now, coming back to the diff. So some diffs were real problems, like real signals, and some of the differences we are keeping on purpose. A simple example is that when there is a syntax error, Postgres points the exact character position in the error message. But since we have the proxy on top, which is doing the parsing, that exact positioning could get varied because the parser is written in Go, and then it's a re-implementation of that. So we could fudge it to match, but then we thought that this is something that we would just live with. And we just capture those things in patch files, which we apply onto the result when we do the regress and isolation matchup. So that we are very intentional about what are the diffs and where we are deviating from the Postgres behavior. Now, that was for the regress, which captures all the single statements. And what about concurrency? So getting the isolation tests to run was also quite a fun puzzle. So these tests work by having several sessions deliberately block each other at various different points in time. And then they ask Postgres, the PG blocking PIDs, using that function, that which backend process is blocking me or blocking this backend. The test checks who is waiting on whom. But think about what that means when you have a proxy and a puller in front. The session the test thinks it owns isn't the real Postgres backend because it keeps shuffling. It's a virtual connection multiplexed onto a pool. So when the test asks about its own process ID, it is really asking about an entirely different PID. The actual lock holder is some other pooled backend the test can't even see. So the assertion just silently compares the wrong things and the whole suit is meaningless. So our fix, again a simple one, is that we use that notion of virtual PID. So at the session start, we stamp this VPID into the application name, which is like a free form, you can set it. Then we install a tiny PGDay helper alongside the suit that translates the client visible session identifier back into the real backend PID at query time. With that in place, the isolation tests were also running end-to-end, completely unmodified, and then again kind of the proxy becomes invisible to them. So now, okay, so results time. A number on its own does not tell you anything. You need a baseline to compare it against, right? And we thought like an honest comparison would be side by side with PG Bouncer, because that's the de facto standard pooling for Postgres. Not because like it is doing something wrong or anything. PG Bouncer is excellent at what it does, and it is battle tested in production basically everywhere. The reason I am comparing it against is that this is the tool we all are very familiar with and we trust, right? So here is a head-to-head comparison with Multigres with PG Bouncer. So in the PG regress, we have like 2 tests. Multigres currently is able to run 164 out of them. PG Bouncer in transaction mode gets you to 155. PG Bouncer in session mode gets 2 to 1. The one test which fails really counts the number of logins, and if you have a pooler on top of Postgres, the number of logins differ, and that is the one test which fails even in session mode, but that's fine. So let's unpack that, what the modes really mean. So session mode passes almost everything, but that's precisely because in session mode, the PG Bouncer pins one client to one backend for the entire session and barely pools at all. It inherits all the Postgres behavior because it is like hardly doing anything in between. The most head-to-head comparison is the transaction mode. It's the mode where pooling actually is happening, where the connections get shared between transactions. And against that mode, that is where we actually see the comparable results. The gap between what we see with Multigres and when we compare it with the session mode is the work that is currently still in flight. So currently we are at 164. I want to call out that this is not like an architectural ceiling. These are just things that we are fixing on the fly, and we intend to reach full compatibility with that. So all of the results are in the repo, so I recommend you to check that. And just to be fair to PG Bouncer, it can claw back some of those test cases by using some GUC variables, like track extra parameters that carries a handful of parameters. But Still, there will be some cases where it is documented that PG bouncer will not work, like withhold cursors, listen, notify, temporary tables, anything which basically needs session state persistence. They will not work with the transaction pooling mode. So if your application happens to stay inside that envelope of transaction pooling, then it is perfectly good and a really good choice. But if it strays outside, then those features will probably silently stop working or just misbehave. Right? So what we do in Multigres to keep them all, so the core idea is that every client connection carries its own session state with it. Its GUCs, its prepared statements, its current role, its open portals, etc., etc. That state is very first class and it travels with the connection. And when a query needs a backend, the pool doesn't just grab any free connection. It routes the checkout to a backend that matches that session state, bucketing connections by their settings. And on top of that, there is a reservation mechanism. So since we have the multi-gateway, which can parse and understand the query, we can automatically figure out whether I need to pin the connection or not. So think of it like a small bit mask of reasons that a connection has to actually pin one top level client connection all the way down to a Postgres backend. An open transaction, a temporary table, an open cursor, or an active listen, all these are reasons why you would end up, like the system would end up automatically switching to session mode instead of transaction mode. The backend is held only as long as one of those reasons is still true. And the instant that they clear, it goes back to the pool to be reused by any other top level connection. So that's the how part, and there is a whole separate talk in our blog series that goes much deep into the pooling part and how we let the session specific states travel. Now here is kind of a summary of the whole talk in one slide, which is that session mode keeps them all, transaction mode gives essentially kind of a lot of them up by design. In Multigres, we intend and we are trying to keep them all irrespective of, like, without the client having to choose one mode or the other, while it is actually still pooling at the end. So the trade-offs. So I don't want to tell you that everything works out of the box because everything has some trade-offs. So choosing gRPC as a protocol between our two services brought us a lot. Real streaming, structured and typed errors, generated client code, a transport everyone understands, but it also took away few things. We gave up the schema on wire flexibility you would get from rolling your own protocol. And as you saw with those bunch of error fields, we gave up Postgres' native error model and had to rebuild it on top of gRPC. The rebuild is a real ongoing work, and it was the right call for us, but it's a genuine trade-off and there is no free lunch. Right. So let me leave you with a couple of takeaways. So these are the lessons that I would want to remember if I was building or evaluating any proxy or pooler in front of Postgres. The first one is that compatibility is a spectrum. It's not a checkbox. Just saying speaks Postgres can mean almost anything. The long tail is what separates a proxy you can actually adopt from the one that breaks quietly. Right? Number two is test with the database's own test. So in case of Postgres, we have PG regress, we have PG isolation, etc., and so does a bunch of other extensions that we intend to support. Pointing it at your proxy will teach you more in just one afternoon than any suit that you can think and write yourself. So leverage the existing suits that are there. Three is that diagnostic fields like errors and notices, warnings, etc., and the fidelity of that is non-negotiable. Every one of those error fields exist because some real tool depends on it. So preserve all of them and prove it with some round trip test or something that all of those fields and all of those messages are actually preserved. 4 is gRPC or any other structured transport is not a free protocol bridge. You will end up rebuilding things you took for granted, so plan for that. And lastly, the one that ties it all together, measure compatibility, don't just assert it. So if you want a long version of this, the architecture, the error model, the cancel trick, all of that in more detail, that would be a bit difficult to fit in a talk. So there is a blog which talks about this whole thing in a detail. You can scan that QR code and the blog is live now. And that's all. Thank you everyone for listening. The whole thing is open source at the Multigres repo. And I really mean this when I say that you should go and try it out. If something breaks or if you hit a compatibility corner that I did not mention today, please open an issue or a discussion. That is genuinely how we find cases we haven't thought of. My contact details are up on the slide. And with that, I would love to take your questions. Thank you.
Yes, thank you for the presentation. Did you measure the impact of this serialization, deserialization during the, yeah?
You mean the performance?
Yeah, the performance.
Yeah, that is still ongoing. Like, I would not want to quote any numbers now because still we are like, just on first, we released the alpha version of Multigres, which is live now, and currently we are in the hardening phase, so we are optimizing it for the performance parts now.
Yeah, I was a little curious, was there ever a point where you considered not using gRPC? Like it seems like you've bought a lot of problems and overhead.
Yes. So that is a good question, and like the philosophy of Multigres was that we are building Vitess for Postgres, and that kind of softly dictated bunch of choices, for example, choosing gRPC or maybe even choosing Go or maybe choosing this two process model, etc. So since even in the code, if you see, we do borrow a bunch of code segments from Vitess, like libraries and all. So having gRPC there helped us like move faster. But maybe we could have done something better, but so far that does not seem like a bottleneck.
D'autres questions? No. Thank you.
Yeah, thank you. Then we can all go to lunch in time. Thanks.